unconventional shales for oil and gas. Some people argue they can measure the value and it's around 0.4, even as low as 0.3. Remember, always larger than porosity. But the Biot coefficient is also going to depend on the size of the process and the time length of the process you're considering. So I put this as a reference, but we're going to come back later on to the Biot coefficient, trying to understand why it is useful and when it is useful. All right, so are we in time? No, we have 10 more minutes. Great. So let's see, where was I? Was over here measuring the Biot coefficient. All right, so now we know how to measure the Biot coefficient. What do we do now? What can we do with the theory of poroelasticity? So I'm going to come back now to our convention of compression being positive. We knew from before that the effective stress tensor is going to be the total stress tensor minus the pore pressure, right? And we call this, thank you, we call this Terzaghis effective stress. We already knew that. But now we have found this new equation which kind of includes Terzaghi whenever alpha is equal to 1. But now that we can measure alpha, we can compute the effective stress using the Biot's coefficient.
Is there a reason why pore pressure is now a vector instead of a scalar? When previously it was a scalar?
Well, it would be, this one is equal to, probably you're right, I should change it, but it should be something like that, okay? So, but I think rigorous.
I just want to make sure we didn't like suddenly have multiple different.
No.
Pressure.
No, but you're right. You're right. If I want to be rigorous, I should write it like this. I just wanted to save some time. So Biot effective stress. Okay, so you may say, well, you now have a better equation in order to know what is effective stress. But poroelasticity is much more than that. It's not just about effective stress. We now have a better equation for effective stress, but with poroelasticity now we can do many things. Poroelasticity is going to allow us to predict, as we had in our equations before, changes of porosity that we couldn't do before with effective Terzaghi's effective stress. Poroelasticity also is going to allow me to compute the quantity which is called undrained bulk modulus, which is the bulk modulus of the porous solid without letting fluids escape. If I don't let fluid escape and I apply compression from all sides, what do you think is going to happen? And therefore, and what is going to happen to pressure? We're going to have a pore pressure change. With poroelasticity, I'm going to be able to predict changes of pore pressure due to changes of volumetric strain. And one more, if I let that fluid move, also poroelasticity is going to allow me to calculate something which goes by the name of squirt flow. That will be the fluid flow induced by changes in bulk strain. So imagine that you have a porous solid. If you compress it in one direction and you reduce the porosity, the fluids are going to move out of that region. And we're going to put all of that into an equation, which is the coupled equation of poroelasticity that we're going to see later on. Before we do that, I'd like to write this equation entirely, and from now on, I hope that you recognize that because we have a pore fluid and it has a coupling with the solid deformation, we're going to have undrained processes, but also we're going to have drained processes. So this is going to allow me to divide poroelastic problems in two types, drained and undrained. What do you think is going to be a real process, for example, of pore pressure depletion in a reservoir? It's going to be undrained or drained? It depends on the permeability of the rock. So it's actually going to be a combination. So a real problem is going to be a combination of these two, okay? But we're going to explore these two solutions as end members of the actual solution. So if we don't do that, I'm doing this because I want to get rid of time. I don't want to talk about time-dependent phenomena now. And in order to do that, I have to either assume that this is drained or it is undrained. And everything in between, you have to put time in it, and that's going to be a combination of drain and undrained. All right, so let's just write the equation, and then we'll call it a day. So we're going to address the problem, the drain problem of reservoir depletion. What?
It's 350 right
Okay, then let me finish the title then. Reservoir depletion. And our objective is going to be to predict the stress path of the reservoir rock as you lower the pore pressure. And this is what we're going to do on Thursday. Okay? All right, guys. See you on Thursday then.